The first thing you have to do with a transformer is to map it out. So looking at this transformer, we got the red and white coming out on this side, and we got blue, black, and green on this side. So we're going to draw that out on a piece of paper. I have red and white on this side, and I have blue, black, and green on this side. So if we read it with a meter set to ohms, we're going to hook up the red and white side. So we're hooked up to the red and white side, and you can see we have 0.7 ohms. So that I've listed right there. So let's go to the green blue side. So we hook up to the green, or the blue, I'm sorry, and the green. And we get, last time I got 63.7, this time I'm getting 63.3, so probably a better connection, 63.3. All right, now what about the black wire? Well, we'll hook up to the black wire from the blue to the black, and we get 32 ohms. So blue to black, 32 ohms. What about green to black? Green to black is 31.6. So we have that. So we can assume that with this side being at 0.7 and this side being at 63.3 ohms, that the higher ohmage is usually always the primary. So this is a center tap primary, and this would be the secondary, okay? The other thing that we have to check is we have to make sure, we know that the green, the black, and the blue are all connected with some ohmage. So we need to check and make sure there's no shorts across the transformer, which means we go to the red and white and make sure that they stay open, and that's good. And how about to ground? And the ground, it's open, okay? So again, to reiterate, we have 63.3, we have 0.7. We can assume that this is the secondary at 8 ohms, and this is the primary. So we'll go ahead and do the test. So what we're going to do is we're going to feed the voltage into the secondary and then read the primary to get the turns ratio. So we're going to hook the A port up to the secondary, and we're going to hook the B port up to the primary. And we're going to set our multimeter to read volts AC, turn the test set on. And some transformers with this particular signal generator, you can't get a full volt. I can go up and I can get 0.8. I could before, but I had to do a modification to stop distortion. So at this point, we'll set it at 0.5. And you can still do that. You could do this test at 100 millivolts if you really wanted to. But to me, 0.5 is pretty easy to get to on this generator. There we go. We'll go with that. 501 millivolts. Then all we're going to do is move the meter. I got this backwards, but it doesn't matter. And check phase relationship that way. So we move over to the secondary and we have 5.456. So if we take this 5.456 and divide it by 0.5, 5.456 divided by 0.5 equals 10.91. Okay, so we're going to go ahead and square that, and we get 119.07 ohms per turn. And if we take that and we're going to put an 8 ohm load on the secondary, so we times that by 8, we get 952.57 ohms on the primary. 952 to 8 ohms. And if you look up the specs of this, this is a Radio Shack transformer that came out a long time ago. They were in the bins. Basically, it says the primary input impedance of this transformer should be 1,000 ohms plus or minus 10%. And guess what? That would be 100 either way. So that would be 900 to 1,100. We're at 952, so this transformer's in tolerance. So let's take a look at this transformer and see what it is. We're assuming it's an audio transformer, but we don't really know. We can look it up, and we'll look it up later, but let's map it out and figure out what the turns ratio is. So I'm going to go ahead back to ohms, and we only have 2 terminals per side. That's it. So we have just a basic, we're going to draw that out on the map here, and we're going to read one side. Interesting. We got 108.7 ohms. I'm going to read the other side, and 87 ohms. And we're going to check across for shorts, and we have an open, which is good. All right. So we don't know what this is, but we're going to look at it anyway. We're going to hook our meter back up to the A terminal. All right. So in this case, we are going to feed the 87 side. I'm going to have to figure out which side it is again. So I had to go back and mark the transformer. This is the 87 side, and this is the 108 side. So we're going to feed the 87 side. So we're going to hook up to the 87 side. And hook up our so-called primary to the B side. Go ahead and turn the power on. And we're going to set it for 1 volt. So there we have 1 volt. So we got 1 volt over on the 87 side. Let's go to the other side. .065, which is odd, and this is You can see I screwed up the color code on these, but just to show you, it doesn't make that much of a difference. Let's move it back. Here we have the color code correct. And we're still getting the same thing, 1.065. So if we take the 1.065 and divide it by 1, we have our turns ratio is going to be 1.065. And you're like, wow, that's really odd. It's a 1-to-1 transformer, so it's probably an impedance matching transformer, which in turn it is. If you look up this part number, this TTC 143LB, you'll find out that this is a 1-to-1 transformer. And it's a matching transformer at 600 ohms. So if we put 600 ohms on one side and 600 ohms on the 1.65, we got 639 ohms. So it's a 1-to-1 matching transformer. Okay, so our third transformer, again, I don't know what this is, whether this is a power transformer. It was just a transformer out of a box in the spare parts. It was not marked, nothing on it. I think it's don't know what it came out of, but let's take a look at it and see if we can figure it out. This time, we're going to use the scope rather than the meter. So you can see we have scope hook up here, and I'll show you the scope up here in a second. But let's map out the transformer first. So we have a black side and we have a yellow side. All right, so what's our black side read? I'm gonna go to ohms, hook up to the black, okay, the black side reads 0.765 K. What's the other side read? The yellow side .9 ohms, which is interesting. Almost looks like another 8-ohm transistor or transformer, but we'll find that out in a second. All right, so we're going to hook the transformer up. Make sure we get our color codes right this time. So we're going to feed the yellow side. And we're going to pick it up on the black side. And now we're going to look at it doing it on the scope. So we have this hooked up to port A. Come up here and look at the scope. Crank that down a little bit. But you can see we have our sine wave, and you can see that it's not the greatest of all sine waves, but it just is what it is, but it works. But we can see our cyclic RMS is 1 volt, and our frequency is around 1,000 kilohertz. So that's great. Now, let's move our oscope to port B. So we've moved to channel B for the output, and we can see our output is 9.6 volts RMS and 30.8 volts peak to peak. So let's do the math. So this one's easy. It shows the turns ratio at 9.6. 9.6 squared. 92.16. If we times that by 8, we get 737 for the primary. So it doesn't seem like an exact replica of the other transformer we looked at. Now if we go to 30.8, which was our peak to peak, divided by 3.16 equals a little bit better, 9.74 squared times 8 equals 760 ohms. So this kind of doesn't look like an audio transformer. I mean, it could be, but it doesn't look like it would be that way. So maybe it is a power transformer, but how would you know that? I mean, it's kind of tough. There's no markings on this thing whatsoever. And if it was a power transformer, how bad would it blow up if you put 120 volts onto it? So this is what I'm thinking in the end. If we take, we know it's 9.6 approximately 9.6. If we had 120 volt input into this and divide that 120 divided by 9.6, that equals about 12.5 volts, which would make sense for a power transformer. Now, I'm reading the inductance here. I got about 5, so L equals 5. And if we want to know the inductive reactance, X of L equals 2 pi FL. So the inductive reactance at 60 hertz would be 6.28 times 60 times 5. .28 times 60 times 5. Equals 1884. So that's our inductive reactance. But remember, this circuit's going to resemble this. It's going to be your DC resistance plus your inductive reactance would equal your ZT. So, and I believe ZT equals R squared plus L squared and the square root of that. So what's our R? Our R, if we go back and look at our R, it was 700 and 765 ohms. So 765, and our L squared would be 1884. So 765 squared plus 1884 squared equals square root of that. So we'd have approximately 2033 ohms. So if we take 120 divided by 2033, about 59 milliamps. And power, we could just take 59 milliamps times 120, 7 watts. Question is, do you think this would handle 7 watts of power? Probably. Or I'd say this is probably a power transformer.